Keen, thanks for your question. The easiest way for me to answer these is to actually give you a set of worked solutions. So I'm going to go through this on the whiteboard app, and I'm going to record the solutions, send them back to you. I hope these help you. So I have the question here in front of me from the mock that you were talking about, and it's got to do with washing soda. Okay, now usually with washing soda, the key part of these questions will always be work out the value of X, and the way in which we work out the value of X, which stands in front of what we call the molecule which represents water crystallization, is to get the ratio between the two parts, the active part which the titration will reveal, and then the water which will simply join the other water molecules that are part of the solution. So anyway, in an experiment, 4.69 grams of hydrated sodium carbonate were weighed out and dissolved in deionized water. The solution was then made up to 250 in a volumetric flask. 20 centimeters of solution were transferred to a conical flask and titrated against a 0.13 molar hydrochloric acid solution using a suitable indicator. So part A, describe the procedure for dissolving the hydrated salt and making up the solution to 250 centimeters cubed in the volumetric flask. Now again, there are 12 marks for this, okay? So I would suggest out of the 12 marks, you have 4 good solid points, which would be made up of the following. So 1, 2, 3 and 4. So you know there's 4 points needed to maximize your marks. Okay, it doesn't ask about weighing. It simply says describe the procedure for dissolving. Now that means as soon as you lift your crystals off the mass balance, the digital scales, what do you do with them? Well, first of all, you've got to make sure that you transfer the crystals from the clock glass or the weighing boat. We use plastic weighing boats in our lab. From the plastic weighing boat into a beaker that contains 100 centimeters cubed of water. However, when you're transferring, this is what I need you to remember. When you're transferring crystals, whether they be dry or whether they be already dissolved, you have to make sure that you rinse the container that held the crystals in dry form or the dissolved crystals. So in 2 situations here, I'm going to be referring to rinse and transfer the washings, okay? And this is the first one. So you're dealing with a clock glass. So you transfer the crystals, the weighed crystal, if you want to put that way, let them know that you've already done that, to a beaker containing 100 centimeters cubed of water. Okay, now deionized water, always good to mention the word deionized, because at least then you know that there's nothing in this particular solution that can interfere with your titration outcome. So deionized water, H2O, and immediately you always say then rinse the boat. The boat is what we hold the crystals in, and transfer washings. Okay, so that's the first one. Now what do we do then? We dissolve the crystals in the 100 centimeters cubed of water. So stir, dissolve, I suppose best way to put it, crystals by stirring. And then you want to transfer these into the volumetric flask. All right, so usually the way in which we transfer them is we pour the beaker into, or the contents of the beaker into the volumetric flask. Now what I think I've always suggested to you folks is use a glass rod to help you. If you pour the solution from the beaker along a glass rod, I'll just demonstrate here what I mean by that. So here's the neck of the volumetric flask, which is quite narrow. Okay, if you have a glass rod in the middle of the neck like that, and you pour the solutions from your beaker like this along the glass rod, what the glass rod does is it helps the solution to go right down the neck, the middle of the neck of the flask, and it doesn't get stuck to the sides. Okay, so the glass rod is a way of helping you to guide the solution down into the volumetric flask. So dissolve crystals by stirring, and then what? Then using a glass rod, pour the solution to the volumetric flask. Okay, now again you're going to say the same thing. Rinse the beaker, KER, and transfer the washings. Transfer the washings. Okay, so now you're on to point 2. Point number 3, using deionized water, H2O, bring the solution up until the meniscus sits on the mark on the neck. So using deionized water, bring the meniscus up until it sits on the mark on the neck. Now again, if you want to demonstrate by a diagram, this is what you mean. There's the mark and there's the meniscus. Okay, so, and it's at eye level, so you've got to make sure it's at eye level as well. So that's point number 3. And point number 4 then is that you stopper and you invert the contents times 20 to ensure, and they love this word, homogenized solution. And that just basically means that the solution is homogenized, means that the concentration is exactly the same from the top and the bottom. The example I always use is you put a spoon of sugar into your tea and forget to stir it. As you drink the tea, the concentration of sugar gets stronger and stronger and stronger and stronger until it gets sickly sweet at the bottom where all the sugar is. But if you stir it, it has the same sweetness from top to bottom right the way through. That's a homogenized solution. Okay, so that would be your 12 marks got for part A. Okay. Part B, what are we asked to do? Part B, name a suitable indicator for the titration and state the colour change observed. Now, that all depends on what two substances we're titrating. Here, we are titrating Na2CO3 against HCl. This happens to be a weak base, and this happens to be a strong acid. Now, in that case, that means that we're starting at a low pH in terms of the acid, and we're not going very much beyond 7. Because if that's a weak base, you might be going to 8 or 9. So therefore, you're working in the lower regions of the pH scale. And because you're working in the lower regions of the pH scale, you're dealing with methyl orange. Methyl orange is always used as the indicator for lower pH titrations. Okay, so methyl orange would be the indicator there. If we were working on the upper end, if we were using a weak acid with a strong base, we'd be using phenolphthalein, okay? But for the lower end titrations, we're using methyl orange. And I guarantee it asks, name the colour change observed, am I right? Name a suitable indicator and state the colour change observed. Now again, when you want to state the colour change observed, state both colours, the before and the after. And just think back yourself, you use this. When you put methyl orange into the base, it stays orange, okay? And we're looking for the change from orange to pink. So there are the two changes, orange to pink. If you remember me telling you, the first hint of visible pink and permanent pink, all right, when the pink is there, it doesn't disappear, that's when you are very, very close. You just overshot tightly, very, very tightly. You've overshot the point of neutralization, but it's perfectly okay from the point of view of a chemical titration. Okay, then what does it say? Name a suitable indicator. Oh, keeps going. So 6 marks for that. Now the 6 marks will be 3 marks would obviously be given for the methyl orange name and 3 marks for the colour change. After carrying out a number of accurate titrations using the 20 centimeters cubed of sodium carbonate solution, the mean titration figure was found to be 20.17 of the 0.13 molar hydrochloric acid solution. The titration reaction is, so here we go, Na2CO3 plus 2HCl react to give 2 NaCl plus H2O plus CO2. Now the one thing you will notice that's missing from this molecule here is the water of crystallization, because only the active part of the initial molecule, if you go right back to the very first paragraph there, Na2CO3.XH2O, the .XH2O is water of crystallization, which is trapped non-chemically bonded water that simply gives this particular compound a crystalline form. Okay, so you'll notice that when they're talking about the titration, they're talking about the active part of that molecule, the Na2CO3. So what the titration is going to reveal to me is how much active ingredient they found in the original number of crystals that you already divide out, the 4.96 grams. So what we're trying to do now by titration is find out how much of that 4.69 grams is actually made up of the active ingredient. And then by subtraction, how much of the 4.69 grams is made up of water. And once we get the mass of both parts in that molecule, we then divide them by their respective masses as given on the periodic table, and we build up a ratio between the two. And that ratio then will give me the degree, that's what we call it at the very bottom, the degree of hydration of the original crystals. Okay, so what are we told? We're told here to, first of all, work out, calculate, part C, calculate the number of moles of hydrochloric acid in 20.17 centimeters cubed of the standard solution. Now what have we got? So I always make it a habit of writing down what they tell us about these things. We have V1, M1, N1, and V2, M2, and N2. So what's the volume of the sodium carbonate? Well, what did we do? Go back to the paragraph there. 20 centimeters cubed of this solution. And the solution we're talking about is a sodium carbonate solution. We do not know its molarity because that's what we're trying to find out. And then we have N1 and N2, which are the numbers that are the coefficients of both species in the balanced equation. Okay, what about the HCl? The HCl, we're told 0.13 molar. And then we're told that we have the titration figure of 20.17 centimeters cubed. Okay, now here's what I need you to remember. If we're asked about the standard solution, it says there the number of moles of hydrochloric acid in 20.17. That comes from these two. So they're kind of taking a little journey through this question. If you use 20.17, think about this, 20.17 centimeters cubed of a 0.13 molar HCl solution, then you will not have 0.13 moles. 0.13 molar means if I had 1,000 centimeters cubed, if I had a litre, I would have 0.13 moles. So therefore what we can say from here is we've got to explain what that is. 1,000 centimeters cubed would contain 0.13 moles. But I didn't use that. I used 20.17 centimeters cubed. And I want to work out how many moles are in that 20.17. So you go to your calculator, trusty calculator, make sure your batteries are working, and then you multiply 20.17 by the 0.13 and you divide it by 1,000. And that ends up telling me that I'm only using 0.0026 moles. Okay, so now at least I know the number of moles in the HCl. Look at part 2, the number of moles of sodium carbonate in the 20 centimeters cubed. Well, here's where I hope you agree with me. The number of moles in both of these to cancel must be the same. But look at the balanced equation. There will be twice the amount of moles. Look at this here. There will be twice the amount of moles of HCl compared to Na2CO3. So the ratio down here is 1:2. So therefore, if there's 0.0026 moles of HCl present, thanks to the ratio, there will be 0.0013 moles of Na2CO3 present in the 20 centimeter cube portions. And the last thing they want to do then is to find out the concentration of anhydrous sodium carbonate in moles per litre. Well, if there is 0.0013 in the 20, so 20 centimeters cubed contains 0.0013 moles, I want to bring this back up to 1,000 centimeters cubed, because the molarity of any substance is the number of moles that are contained in 1 litre of that particular solution. Okay, so if 20 centimeters cubed contain 0.0013 moles, 50 times that. So if you want to go from 20 to 1,000, you multiply by 50. So this one here, I'm also going to multiply by 50, which will tell me that divided by 2, multiplied by 50, that we're told the molarity is 0.066 moles. And that gives me the molarity of 0.066 molar solution, or moles per litre. Okay, now, and that's what they asked me. The concentration of anhydrous sodium carbonate in moles per litre, now in grams per litre. So this is just a matter of changing from moles to grams, which I do by multiplication. And I want the grams per litre of the anhydrous sodium carbonate. So that means I have to work out the mass of Na2CO3. That's the anhydrous one, doesn't have any water attached. So we go to the periodic table. Sodium is 23, so 23 and 23 is 46. Carbon is 12. And oxygen is 16 3 times, which is 48. So the mass of that is 106 grams, as given on the periodic table. So you're going to multiply here by 106 grams. So 106 multiplied by 0.066 comes out as 6.99. So 6.99 grams per litre. So that's the second. So there's the first answer that they were asking for, moles per litre. There's the second answer that they were asking you for in terms of grams per litre. Now, last part, part D. Calculate the weight of water in the original sample and hence the percentage of water of crystallization in the hydrated sodium carbonate. So what did we do? we put 4.69 grams. This is what we're told at the beginning. We put is it 69 or 96? I have my glasses. 69. 4.69 grams in 250 centimeters cubed. That's what we did at the start of the experiment. Now we put in 4.69 grams of the hydrated stuff, Na2CO3.HCl. Okay. How many grams did this particular experiment find in the 250? Now, the experiment found 6.99 grams per litre. So what I'm going to do here is I'm going to divide by 4 to find out how many grams of active ingredient was present in 250 centimeters cubed. And then that means I can compare these two, because you have to compare like volumes with like volumes. Okay, so 6.99 divided by 4 tells me that there's only 1.749 grams of active ingredient in the 250. Now, how much did I put in? I put in 4.69 grams. So 1.749 grams is the Na2CO3, which means that the difference between these two here, so 4.69 minus the 1.749 comes out as 2.941 grams is water, because these two together have to be exactly the same mass as the combined water of crystallization with the active ingredient. Okay, so both of them, now I have the mass of both. So what I've got to do now is set up the ratio, Na2CO3 to H2O. We've discovered that there's 1.749 grams of Na2CO3 and there's 2.941 grams of water. So what we're going to do is divide them both by their own respective molecular masses in order to bring the playing field level. Okay, don't forget, water and Na2CO3 are both different size molecules. So therefore, to make sure the ratio works, we divide each one by its own respective mass, which is 106, and here this is 18. So 2.941 divided by 18, and that comes out as 0.1634, and 1.749 divided by 106 comes out as 0.0165. Now I think you can see straight away what's going to happen there. If I take the smallest number and divide it into itself, it's going to go in there once, and this is 10 times the size of the original. It's not even maths involved. So the ratio that we have is for every molecule of Na2CO3 that exists, I will have 10 waters, and that is known as the degree of hydration of the original crystals, and that's what they asked you for in part D. So I hope that helps. That's the question finished. I hope it helps you. It's bringing you around a kind of a more stoichiometric view of the titration, because they're asking you about how many moles of hydrochloric acid are in the 20.17 of the standard solution, how many moles into 20 centimeters cubed. It's all got to do with ratios. So you go back and you work out the fact of the molarity of the sodium carbonate solution, or the HCl, there it is there. Work that out, work out how many moles are present at 20.17, which is 0.0026 moles. You then look at the ratio between the HCl and the Na2CO3, which you discover is 2:1. So therefore that number of moles must be twice what is present in the Na2CO3. So divide that by 2, and that's where you get your 0.0013. And once you've got the moles of both of them present, well, then you work on changing them back into mass, bring them up to mass, moles per litre, grams per litre, etc. And then you finish the question off by looking to see, okay, well, what did I dissolve in the original solution? 4.69 grams in 250. What did the titration discover? The titration discovered there's only 1.749 grams in 250. So what's the difference between the two? And from the difference between the two, then we work out the ratio in terms of the mass. 1.749 grams of Na2CO3, 2.941 grams of H2O. Divide them both by their respective relative molecular masses, and then from that you build the ratio by division. Hope it helps. Any further questions, give me a shout.